Hi, I'm Kishan. Today I'm going to give you a quick overview of how engineers approach heat transfer. Now, the first thing to know is what are the types of heat transfer? Well, there's three main types of heat transfer. The two most often ones that we deal with are conduction and convection. And the odd man out that we also deal with is radiation, which I'm sure many of you know. So an easy way to think of all three of these types of heat and transfer in one quick, easy example is to think of, boiling water over your stove or a fireplace. Let's just use the fireplace because it's a little more easy to understand. So you have your fire, really poor example, but so the first type we're going to deal with, which is start at the bottom, is radiation. So as the fire is heating up, it's basically emitting particles that transfer energy. So that's what you're going to recognize as radiation. So radiation is the transfer energy through particles or waves or rays. So easy way to think of it is just think of light. So light or fire, they emit radiation, and that's how you get your heat transfer. So now if we have our pot here, let's just get a 2D cross section of your pot, and let's say it has some water in it. Now, if we just zoom in a little bit here, right? First, what you're going to notice is the pot is going to get hot. It's going to absorb the heat. So as the heat transfers through the pot, right, the pot's going to heat up. So when heat transfers through a solid, this is what's known as conduction, right? So as the pot heats up now, and we have the water in there, as you know, it's going to start bubbling as it heats up. This is heat transfer through the water, which is known as convection. So the whole system we can see, so as the fire is burning, we have radiation heat transfer. Radiation transfer heats up the pot itself, the metal pot, and that's conduction, and then convection. So the easiest way to think about it is radiation is any sort of transfer through no medium, so through rays or particles. Conduction is through a solid medium, and convection is through a fluid, and that can be water or it can also be a gas. So water or gas, and this one would be for a solid. Now, as engineers, if we go to the back of our napkin here, as engineers, when we deal with these kind of problems, let's say for example we're dealing with a wall, when we try to think of walls, we usually think of thermal resistances. So first thing you're going to notice is let's say there's some air here, and it's at a certain temperature, right? What's going to happen is the air is going to have a temperature, and heat transfer happens from when you have a high temperature and a low temperature. So if there's high temperature here, the heat's going to want to go to the low temperature zone. So we call these heat transfer regions through some sort of medium thermal resistances, if you remember from your electrical resistances. So in this one, this will be the thermal resistance of air, and it's going to have conduction. So this R for resistance, and it's going to have convection because it's through air. If you remember from the back here, the medium air is through some sort of fluid. So we have convection to the air, and then we also have resistance through the solid wall, and this is going to be more conduction. But it doesn't stop there, because now as it passes through the wall, it's going to have resistance through the air again. And then this is going to be your T infinity. Okay? So basically you have a really hot air here, and then a lower temperature over here, and that heat transfer is going to travel this way. So basically what we can do, we can assume that if we're in a steady state, which basically means nothing is heating up, the temperature's not increasing, the heat's just passing right through it. So the heat transfer is going to go from here to here. And this is how basically we analyze systems. And as a little bonus, if we include radiation, and oftentimes with the temperatures that we're dealing with, radiation is not that much. But if we are, just remember from your thermal resistances, we add a parallel branch, and this would be your radiation. It's kind of a weird branch. It's better if we just do this. Here we go. And this would be your radiation. So these two are parallel in branches, and this would basically be your system. And as you have different types of system, like a sphere or a cylinder, you're going to deal with different directions of thermal resistances, and you'll have different equations. And that's all. Thank you very much.